that. It may be it may be chocolate chip cookies. It may not. Some of you know what my chocolate chip cookies are like, but you know, it is what it is. It's just, I'm really happy to see you. And I like, yeah, you know, the civvies isn't going to help you. The point is you got to wash your clothes every day and you're allowed to wear your tracksuit. And I'm already going to be having, you are correct, Gabby. I'm already gonna be having issues with the boys' hair, but I do understand that the beauty industry is not available. My hair needs help. I need to see my hairdresser. Anyway, oh, Angela, I love you, just so you know, but I love all of you. Moving on. Yes, it is, Isabella. Oh, I don't want to see Lee's hair. But that's why we're giving you the choice. That's why we're saying you can wear your tracksuit one day, you can wear your school uniform the next day, even though you're not doing phys ed. Okay, I think it's just, and by the way, that was my idea. That was my compromise. So I have my moments. So what we need to do today, please don't talk to Mrs. Muller's classes. I'll come back to you, Isabel. I'll come back to you now, but you are washing every day, sweetie, but you've got the time for it to no, you can't grow. Yes. Oh, I wouldn't be able to see them. Isabella, the point is you've got time to let it to dry. Not everyone has, but not everyone has a tumble dryer. Like I know if I don't have a tumble dryer. So even if I wash this, so I could wash when I get home. I love your mother, Aura. Mine wouldn't be dry by the next day. I also don't have anywhere to hang it out outside. Okay. They won't dry in one day. Carl, let's not push it before we get back. Okay. Let's not push it. I'm not getting into this discussion. The point is, I'm excited to see you on Monday. Not sure how I'm going to get up in time, but I'm excited to see you. Moving on. Okay. Mrs. Muller's class is a little ahead of us. Please don't stress about that. I'm not worried. Kaylee, coming back to your assessments, I'm very beyond pleased to announce that it is definite that we do not have to do any more pracs, and I'm beyond happy about that. Technically, we don't need any more cycle tests, but I am going to ask for a cycle test to put into your SBA because if I use the one you wrote in the first term, it's a bit of a nightmare. Okay, we all know you didn't do so great, so I want to rather give you another chance to do a cycle test that I can put in place of that. Okay, because I don't want to use those marks as they are. I don't think it's fair on you guys. All right, but that's another story. But the thing is, we don't need to do any more pracs. All right. Electra, I'm going to ask. Whether I get it is another story, but I think we will. Okay, so I'm going to beg. I'm going to send Mrs. Pierce a letter and say, I'm going to beg. I hope not. Well, actually, I don't see you first. Waiting area is closed, Jordan. Okay, you may not go into the waiting area. You're too close. So, on that note, we need to do work. On Tuesday, okay, when I saw you, there we go. On Tuesday when I saw you, we were looking. There we go. All right. Sports cancelled, Carl. Sports cancelled. Okay, don't even go there. We're not doing this again. We spoke about this last week. So, we need to go through where we were last time because we need to get to some more questions. Okay, so now we need to actually do some work. No, you don't want to, but we're going to. So we were on this on Tuesday, and I know it caused a little bit of some of you were quite freaked out by it, and I'm sorry. I think it's just because of the way I laid it out. Okay. Xavier. Okay, I've got a pack here. Okay, so here, all the notes that we have been using, plus the start of the next section. Okay, it's here. After our lesson, I'm going to school to put that in for printing for you guys. So yes, you will be given them. All right, so I know some of you had printing issues. Not. Okay, don't worry about it. So let's focus now. Okay, so when we look at, you're welcome, Xavier, the intensity of EM radiation, what they mean by intensity, guys, is how bright the light is, how bright it is. So they're increasing the amplitude of the wave. They're keeping the same frequency, but they're increasing the amplitude. If it's a low intensity light, so it's dim, okay, what that means is the electrons will still come off, but there will be fewer of them. Low intensity light means that there are fewer photons, okay? If there's fewer photons, there's fewer collisions. Fewer collisions mean that there's fewer electrons that can be taken off, okay? Smaller current. Current, flow of it's the rate of flow of charge. So current measures how many electrons move per second. So we have a smaller number of electrons moving every second, we have a smaller current, okay? If we increase, so now look at the difference in the way the diagrams are drawn. Those little squiggly things over here, that represents a photon if we think of light as a particle, okay? So if it's low intensity, it's dim, we have fewer particles. When it's high intensity, we have lots of particles, okay? So now more electrons will come off, which means we have more electrons per second, but we have a greater current. What's really important with these two, okay, and this is what I need you to get. Because we didn't change frequency, the speed at which the electrons are moving is the same. It's the number of electrons that's changing, okay? It's the number. Why is photoelectric effect important? And they're going to ask you this. They're going to go, what's the point of the photoelectric effect? It suggests that light consists of particles. If we didn't have the photoelectric effect, then the electrons wouldn't come off. Okay, so it says just that light is a particle. So light must have this dual nature. So it doesn't, sometimes it's going to behave like a wave, and sometimes it's going to behave like a particle. Okay, it's got both natures. Interference and diffraction, which we did last year, provide evidence that light is a wave. Okay, the photoelectric effect provides evidence that it's a particle. So scientists are going, it's both. Okay, Max Planck, who is where we get the Planck's constant from, and Einstein, and a couple of other guys, they're the ones who put this all together, okay? Yes, Electra, I did. So if we don't change the frequency of the light, then the speed stays the same. But if we change the intensity, then the number of electrons is different. Okay. So I want you to try this activity first on your own before I do it with you guys. I think it's important that you try work through this, okay? Don't stress too much. I'm going to let you take a picture of it for those of you who don't have it. All right, I want to do the last bit of theory so that tomorrow, yes, the speed of the electron, Savannah. So it's how fast they go. That stays the same if the frequency doesn't change. Okay, but I want to let you take a photograph of this screenshot. I desperately want to finish the last bit of theory and then tell you which ones are the worksheet we're going to do. So tomorrow we can just work through being able to do questions. Okay, so over here, page 33, there's the, oopsie, wrong one. If you want to take a screenshot of it, I just wanted you to do, let's just check, question 1 and 2. Okay, all of these questions rely on you using this equation. Okay, and of course, sometimes with these, remember, you may need to use the fact that E equals HF, and that's WO. WO is HFO, and Emax is a half mv squared. Okay, and of course, if we don't have frequency, you need to remember that we have hc over lambda. That I'll pull it up in again in a second. Isabella, give me a second. Okay, and remember C equals F lambda. So I'll tell you what I'm going to do. There we go. So you guys can take a screenshot of it quickly. While you're doing that, for those of you who handed back your assignments, because there's lots of you who didn't and then ran out of time, you should have got it back, and you should have got it back with comments about what you did wrong, what you didn't, why you got the answer wrong. I did realize, and I don't know what went wrong, and I'm going to apologize for those of you who really like to do well, and then you did that and when I didn't know what was going on. Something obviously went wrong, and we're still learning, so please be patient with us. Something went wrong with when I selected for the auto marking what was the correct answer, because I promise you, I did not get all of those wrong. Okay, so for a few of them, sorry, I'm just fixing my socks. For a few of them, I was like, no, there's no ways what I said or what it registered as the correct answer was the correct answer. So you'll see that your marks changed. Some of you got 100%. Yay! Some of you just made very silly mistakes. So please don't worry about it. I'm actually quite happy about that. Okay. Isabella, are you good? Can I move on? Everyone got it? If I missed a conversation, no, there we go. No. Is Isabella with me? Oh, okay. Isabella, if you're struggling with your Wi-Fi, and I know, okay. Oh, sorry, sweetie. Can you not see I don't know. Log off and then log on again. It might help. Can you not? Is it just? Are you guys all frozen? Okay, so I don't think then it's yours. It's mine. Then it's mine. It's not yours. Okay. Can you see it? So you good? Gotta love the Wi-Fi. I'm convinced the internet has now had enough of all of this. Nothing's moved, by the way. Okay, it's been left on this for a while. So don't stress if you think your screen is frozen. I haven't done anything for a while. Okay. So don't worry about it. All right. So let's go here, are back here. So now you can too. Okay, so we've moved things. Brilliant. We're going to do one more thing that explains that light is a particle. Remember in Doppler, we spoke about the spectrum, the emission spectrum, the absorption spectrum. Okay. Okay. 2 seconds. There you go, Luca. We spoke about the spectrum. How those spectrums are created is quite important. Okay. And that's got to do with the fact that light is a particle. And we see it with the way that electrons move in an orbital. Okay, so you know that electrons have a specific structure. You know that when we look at the structure, you did up-by diagrams, you did valence electrons, you did all sorts of things. But you also know there's energy levels. Electrons can move between, you're welcome, can move between those energy levels. We, for bonding and for chemistry points of view, say that they stay in one place, but in reality they don't. Okay, so we're going to look at the different spectras. You have all seen at some stage a continuous spectrum. Okay, so when white light is refracted through a prism, it produces this nice continuous spectrum, a rainbow. Okay, just in terms of the definition of a spectrum, by the way, in your Doppler effects question, I said the question was, what is the one word or term we use for a range of frequencies and wavelengths? It's spectrum general, not absorption or line or electromagnetic, because I didn't say it was sound. Sound can also have a spectrum, okay? But this is a continuous spectrum. So you know that we get the visible light spectrum, okay, which goes from violet to red. You all know this. Hopefully you know the colors of the rainbow. You do not need to know the actual values of their wavelengths. Okay, you do not need to know that. So you don't need to know that red is around 700 nanometers and the back end ultraviolet, well, as we're going in, there's 400, okay, for the violet. You don't need to know that. What you need to know is that red is the long wavelength, violet, blue, the short wavelength, okay? This is a continuous spectrum because there's no gaps, okay? There's no gaps between them. They just merge. They sort of schmoozle into each other, okay? Then we get something called a gas discharge tube, which you have all experienced. That's what, you know, in my classroom and in most of the classrooms, you get those long fluorescent lights. Those are gas discharge tubes, okay? That's what they're called. What is happening, okay, is that we provide a current. That current allows electrons and positive ions to move backwards and forwards in the tube between the anode and the cathode, and that movement causes light, okay? And it's a gas at a very low pressure. The light happens because by adding the electric current over here, okay, we're actually giving extra energy to the atoms. The electrons take that energy. Ooh, sorry, Electra. I forget. I get excited. Sorry, sweet pea. See, I need to see your faces so I can see the look of utter, don't know what's going on. Okay, so the light, I mean, you know, we switch on the light. In fact, even your new lights, energy saving, most of them. Okay, I'll get back there, Lauren. Sorry, guys. I know. I got so excited. All right. Slow down, Miss Fearless. So, grade 12s. This is what happens here. We supply energy by when we put in the electric current, okay? So the volt here, this supplies energy because it's chemical energy becomes electrical energy, right? That electrical energy gets transferred to the gas inside the discharge tube, okay? Now, this is just a long tube that has a gas in it, okay? That gas, the electrons then get excited. So by providing energy, what it does is that it gives energy to the electrons, and the electrons get excited, a little bit like me just now, okay? The electrons absorb the energy that they're given, And then they give that energy away. They can't keep it. All right. When they give the energy away, we produce light. So that's how fluorescent lights, light energy saving devices, they all do the same thing. Okay. So we get light from it. When we direct the light that's given in a specific way, we get those spectrums that I showed you when we were doing redshift and blue shift. Okay, so we're going to look at two different ones. We get line emission spectrums and line absorption spectrums. Okay, every element gives off a specific spectrum. It's its DNA, it's its fingerprint. Now, if we take the light, yes?
Do we need to know this drawing or this diagram?
No. Okay. That was Michaela, hey?
Isabella,
No, Isabella. Okay, sorry, sweetie. No, sweetie. They might just know what it looks like, but they're not going to ask you to draw it. They might put it in the question just to give the question context. Okay. You good? I'm going to take that as a yes.
Yes, thank you.
It's all right. I forget about the lag. It's quite frustrating. Now, if the light emitted by gas discharge tube contains hydrogen gas, so in other words, inside this tube, I have hydrogen gas, and we put it through a diffraction grating. Now, all a diffraction grating is, grade 12s, is it's a piece of material basically with an incredibly thin slit in it, which then the light will pass through it and bend. We did a little bit of diffraction last year, okay? So the light bends and we get a spectrum. Now, this is important. We don't get a continuous spectrum because what has happened is the electrons in the hydrogen atom can only absorb certain frequencies of light. The rest pass straight through. They don't really care, okay? And in reality, scientists have no idea why. Okay? So we get a separate lines, okay? So this is the spectrum for hydrogen. You do not need to know this spectrum, okay? So please don't go and learn it. But hydrogen gas will always give us, yes?
Sorry, I just wanted to ask, if they had to ask us why is it no longer continuous, what would we say?
Because it's only certain colors. So it's specific colors that come out. Can you see these gaps? So it's not continuous. You good, Electra?
Yes, I am. Thank you, ma'am.
Okay. So we get parts of it, and hydrogen will always give me this. No, McClubber, these notes are there. These notes are in the files. They're there. You'll find them. Savannah, which part do I need to repeat? Don't say all of it. Oh, the bending thing. Okay. So remember, the best example is the one I did with you last year, where if you're driving at night and you look through the windscreen and you look at the street lights, they look like there's a halo around the street light. That's because of diffraction. So when light passes through a very thin slit, it bends, okay, to take up the space through it. We did that last year, so it diffracts. So that's the bendy thing. It's not continuous because there's gaps. So there's black gaps here. So when you look at the diagram, you can see there's a color, then there's a black gap, then there's a color, then there's a black gap, then there's color. Okay, so it's not continuous. They don't just smush into each other. They actually have only specific colors come out. Okay. Hydrogen is the simplest spectrum. you're welcome. The more electrons and the more energy levels in a element, so the more complicated the element, the more colors they get. Okay, there's helium. Now, helium only has one more electron compared to hydrogen, but hydrogen has 1, 2, 3, 4 colors. Helium's got 1, 2, 3, 4, 5, 6, 7. Okay, and it's very different to hydrogen's. It all has to do with the electron structure. So the nice thing about this, the emission spectrums do two things for us. Number one, it reminds us or helps us prove in some ways that light is a particle. And number two, it almost proves Niels Bohr's theory about energy levels. Okay? Because we've now got to explain, why do we get those colors? What is it that's happening inside the atom that allows us to get those colors? Okay? And I've said that to you already. So this is what's happening. Electrons, so let's start, I want it to be here. When an electron is in or an atom is in the ground state. So electrons are sitting in the energy level they need to normally sit in. Okay? They're happy. They're like, oh, we're chilled. But then we give the electrons energy. How do we give them energy? By passing heat through it, by putting the voltage over it, we give the atom energy. What that does is it causes this little electron over here to jump. So it goes, oh, I got energy, and it jumps to another energy level. Okay, so in here is the number of the energy level. So this is like energy level 1, energy level 2, 3, 4, 5, 6. Okay, there can't be more than 7. But this electron absorbs energy. So it takes the energy that it was given. It can't stay there. So this is a little like you are in your normal state. You decide you need a boost of energy, heaven forbid at this point, and you drink an energy drink, okay, which I know as teenagers you drink way too much of, but you have an energy drink. You get lots of energy and you're bouncy, jumpy, up and downy, pretty much like me if I've had too much coffee, though I'm not sure that really ever happens, but you can't stay there. Okay, so the energy it's absorbed, all right, so now it's taken energy, it's got to go somewhere. So what happens? The electron now jumps down. So now it's in this excited state. It can't stay here. This is so unstable. It now, and I'll explain all the rest, it now jumps. It goes back to an energy level. When it goes back down, it throws out energy that it was given. We see the energy that's been given off as a color of light because it's a specific frequency. Okay? When it's here, it's unstable, very unstable. And we say it is excited. So it absorbs energy. There's a very unique amount of energy between the energy levels. It's not random. Okay, it's not just, oh, this time when it goes from the 1st to the 6th, it's going to absorb 12 joules of energy. Next time it's going to absorb 13. It's not, it's very, very specific. Okay, which then means when it jumps down to another energy level, it's also specific. Some of you have now gone, but now there's a problem, and I'm hoping you noticed. In this third diagram, do you notice it didn't go down to the first energy level? Okay, so if we look back over here, and if we go here, okay, I showed the electron going from the first energy level to the 6th energy level. And I said to you, that's all the energy it absorbs. It's not going to give that energy off. But if you look at the next slide, it only went down to the 2nd energy level. It doesn't have to go back down to the ground state straight away. It can transition. It can go from one to the other. And there's a whole series of lines that have to do with this. There's a whole bunch of graphs and things that allow you to make predictions, but we're not worried about that, okay? So basically what I'm saying to you is this electron has choices. It could have gone down to there, okay? It could have gone down to there. Each of those transitions relates to a color that you will see on the spectrum. So that's why it's unique, why it's like a fingerprint, okay? And the color is the difference in energy between this state and that state. So if I know what that energy difference is, I can work out what frequency it is. We'll look at questions, don't worry, okay? And that's the electron transition. That allows us to get a emission spectrum. Emission means that it's given off. We will see a color. Okay?
Ma'am?
Yes?
Are you saying that the color is the difference between the different energy levels?
Yes.
And you said something before that about, you said something like each level represents something.
Okay. So, Lauren Rose is asking the same question, okay? When we look at it, so each level, so N6 has a much higher energy level than N2. So for it to go from the 6th energy level to the 2nd energy level, it must give off a certain amount of energy. The amount of energy it gives off translates to the color we'll see, because remember, E equals HF. So the difference in energy is E. That means we get a certain frequency of light. I'm hoping that helps you guys. Does that make sense now? Give me a thumbs up. Yes. Yes,
I just
Lauren.
want to ask, when you said now that it's the difference in energy level.
Yes.
So, would we have to work this out in a calculation?
Yes. Yes.
So, like, would our E be, let's say, like energy level, I don't know, 6 if they give it to us, minus where the electron ends up, and then you would get your answer.
Yes.
Okay.
Absolutely that. So they'll tell you, say that here it's 1,6, say, times 10 to the minus 19. I'm making up numbers here. And this is 1,6 times 10, which would not be possible, but let's just go with it, minus 20. And then you'd have to minus those two to get E. Yeah, absolutely.
Ma'am?
All right. Yeah.
I am a little confused because I'm kind of getting the idea that two different things determine the color, and I don't know if that's correct or not, because you're saying the distance between the levels determine the color, but then you're also saying that the amount of energy given off determines the color we will see. So I'm just trying to connect that.
The distance represents the difference in energy. Okay, so because now I've got all sorts of things, so let's take all of this off. If the electron moves from here to here, so from 6 to 1, it's a bigger energy difference. So it'll give off a certain frequency of light, and it'll be a different color than when it goes from 6 to 2. So how many energy levels it jumps between does determine the color as well, because how many energy levels it jumps between determines the amount of energy change it has.
Okay, thank you.
Okay, no, we're good. This is
Ma'am?
important that, yes?
Sorry, just one more question.
No, fine.
I just want to ask, you said something about the frequency. So when we determine the energy, does that mean, like, I don't know how to put this in words. It will give us a certain frequency. So would we have to work that out? So, like, let's say you gave us energy and you said, like, work out the, I don't know, frequency, Would we then do that equation, E is equal to HF?
Yes.
Okay.
Yes. We
Thank
good?
you. Yes.
Okay. All right. No, ask. I want you to ask. Okay. So we get our unique ones. Why is it important? Which is what I've told you. Tells us that we have energy levels, and you know what? I don't want to do it at atomic absorption because I think it's going to confuse you for now because it's slightly different. So, grade 12s, and we've got 2 minutes left. I'm going to leave it there so you can mull through that. What I would really like you to do for me for tomorrow, so that once I've done the absorption spectrum, I can mark it. I want you to do that exercise, okay, which I showed you, this one, which, there we go, you took a screenshot of for me, okay, and then we'll carry on with that. All right, and I know in the morning it's ridiculously early, but it's okay, we're good with that. Okay, so we are done for today, okay. Hopefully you've got everything you needed. My cat has said hello again. I'm going to stop sharing my screen.
Ma'am?
Yes, I heard. Yes, who am I talking to?
Electra, ma'am.
Yes, Electra. How can I help you, sweetie?
Sorry, I'm so full of questions today.
No, it's fine. Ask.
I wanted to ask if I can ask something about the Doppler effect.
Sure.
Just with that activity that we had to do, I'm not grasping the concept like completely. So those last few like theory questions, the ones that don't have answers, so 5, 6, and 7. I don't know if you want me to read it for you, or if you can like tell me after like the lesson.
Well, if anyone else doesn't have questions, then you guys can all go, because then let's just sort it out. It might be easier if I'm talking to you.
Okay.
Then, yeah. So read them out for me, sweetie.
Okay, so the one says a listener moves away from the source of sound.
Yeah.
Use the equation for the Doppler effect to explain whether the listener hears a higher or lower frequency than that emitted of the source. I think I understand this one, but I just want to make sure that my answer is correct.
Okay, did you not get was there